Welcome back, students. We have been talking about light as a wave. We talked about reflection and refraction by treating light as a wave. And we also saw the Doppler effect. Now we are getting a little deeper into the lesson. We will soon be talking about interference and diffraction. But before we do that, I want to talk about something else. I want to finish this foundation of light as a wave. So I'm going to talk to you now about the coherent sources. There's an idea called as the coherent sources. This is very critical in understanding interference and diffraction of light, which we will be talking about a little later. You need to understand this idea first. But before, again, getting to talk about light directly, I want to give you an example. I want to do a small thought experiment. Imagine this. Imagine that there is a toll gate on a highway. Okay? So there is this toll gate. And further imagine that there is a train of cars starting from this place. Let's say I call this as place 1. Okay. And they move to the toll gate here. Okay. So one after the other, the cars come. They all move with the same speed. Speed is same. And now, let me take another place. P2. And from this also, cars move with the same speed as these cars. Then they get into this toll gate. I'll probably make it shorter. So this is a line of cars, and this is also a line of cars. Okay? They're moving towards this toll gate. They all travel with the same speed. Okay? So now let me take the first car. I'll take the first car here. The first car is going to start from here. And there is, at the same time, the first car from here starts. You can clearly see that this distance is smaller than this distance. Let's say if I say that this is, the distance is d1 and this is d2. d1 is smaller than d2, you can see that. And I told you that both the cars are both these lines of cars. Okay? They travel at the same speed. And the other thing is that the cars are of the same length. Okay, the cars, the size of same cars. Maybe you take, say, Hyundai i20 or Maruti Swift, not Desire, Maruti Swift, something like that. Cars, they are all the same model cars, so they have the same size and they travel with the same speed and they travel continuously. Okay, so same size and same speed, but d1 is smaller than d2. So take the first car. This will reach the toll gate first, and this car would not have reached there yet. This would have reached first. Then maybe the second car would reach there. This car would not reach there yet. But then the third car reaches there. This would probably not have reached there yet. And maybe when, say, the seventh car reaches there from this line, seventh car from this line reaches there, then the first car will reach there. Okay? So seventh car, if we take two lines, line 1 and then line 2. So first car reaches, nothing. And then second car reaches the toe. Third reaches, fourth reaches, fifth reaches, sixth reaches, seventh reaches. And when seventh car reaches there, then the first car from here reaches the toe gate. And then eighth car, then second car, then ninth car, third car, 10th car, fourth car, 11th, 5th, so on. Until this point, there is only one line. But from this point forward, there is no difference. You see, both lines, the cars from both the lines are meeting here. Okay? So, we are going to talk about a case where this condition is met. We are not talking about this. This is for a very, very, very short time. Right? It's very, very, very short time. But then, if cars keep coming, then there will be one car from here, there will be another car from there. One car from here, another car from here. There. So, like, this will continue. So, you may not probably like see both cars for the first few seconds or so. But after that, you will always be seeing two cars from here. So, you wouldn't even know which line started, which start first, or like which line has a shorter distance and stuff like that. Okay? But once this condition is arrived, then this state of affairs is going to continue. So for every car here, there will be another car here. Initially, there will be a car. Okay? I want you to understand that first. And we are talking about this. We'll ignore that, we'll talk about this condition. Okay. Now, when they reach, how will they reach is a question. Okay, for example, if this is the point, let's say this is the point, this is the toll gate, okay? So, the car from one line reaches here. Then the car from the other line comes here. Okay? You see, if this reaches here, like if the middle of the car is at that point, then the front of the car from second line may be at that point. I hope you are able to understand what I am saying. So this is the point of reference. So the car from one line reaches here. See, it is possible that both of them reach at the same time in the sense that, when the front of this car and then the front of the other car meet at this point at the same time. And it is also possible that the middle of this car and the front of this car cross this point at the same time. It is also possible that when the back is at this end and maybe like this, the car is just entering here. That is also a possibility. Or it can be otherwise. Maybe when you see a car from here would have just crossed, and this may be the car from the other point, that line may be entering here. Something like this. Anything is possible. Okay? When I say the two cars cross that point at that time, it doesn't mean that they are, when the front of both the cars are at that point at the same time. It's like, it could be like this. And then for the next car, again, when the middle of that car is at that point, then the front of the next car would be at that point. Then the next set, then the next set, then the next set. So likewise, when they meet here, when they meet at this point, it is possible that this car and this car meet like this, or it is possible that first car is like this and then the second car is like this. Okay, you can meet like this. So when the fronts of both the cars meet here, then the middle will also be the same, then the back portion will also be the same, because you said the size of the cars is the same. Okay, in this case, when probably the windshield screen is meeting that point, then the front could be meeting the same point here. Then if this happens, you say that there is a delay, but then the delay is going to be continued for all the other cars, right? The next pair will also meet like that. The next pair will also meet like that. The next pair will also meet like that, because you have to travel this distance, and both of them are both these sets are traveling with the same speed. So you will cross a certain distance in some time, and you will cross this distance in a different time. So you see, eventually the difference will be maintained for all pairs. Okay, if it is like this, then you say that both these lines are coherent. They can meet, their fronts can meet, or the middle of one car and the fronts of the other car can meet. And the front of one car and maybe the back of the other car can meet. But notice that whatever happens to one pair will keep happening for all the other pairs this time. So however these two meet, these two will meet the same way. 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 So whatever difference the first two cars have, that is the difference the next, all the remaining pairs will also have. I want you to understand this. When this happens, I call this as coherent. Okay, think about it. For this to happen, what are the necessary conditions? One, the cars must be of the same size. Okay? You started from this point, you starting from this point, and this distance is fixed, and this distance is also fixed. Okay, and the cars must have the same size here and here, and they travel with the same speed. That's important. They must have the same size and they must have the same speed. In that case, then this condition will be maintained. What if the cars are not of the same size? For example, you have, say, Desire, or maybe like we have Swift here, and then you have Swift Desire here. So it's a bigger length, right? And this is a smaller length. Then, suppose this meeting happens here. Okay, it is like this, right? One is Swift and the other one is Desire. So this is Swift and this is Desire. So look at this. So this size, they meet here. But then you see, there is a difference. Now the next car, the next pair won't meet at the next pair won't meet like this. The next pair, how will it meet? Okay, I shouldn't have erased that. But the next pair will meet something like this. Okay, I'll draw it here. So, okay. The next pair, the next car is going to have, if it is here, then because this is smaller, the next car would have come a little closer to that, right? Anyway, so this would be somewhere here. the next car. You see, the pairs don't maintain the same difference. If they are the same size and if they travel with the same speed, then the same difference between the front portions of those cars would be maintained. But if these cars are of a different size, even if they travel with the same speed, the first pair may meet like this, and the second pair may meet like this, and the third pair may meet like this, and maybe the fourth pair again will meet the same way as the first pair. So there is this LCM thing, right? The difference in sizes, the LCM. So first pair may meet. For example, like one car is thrice the size of the other car. Okay? Then when you start with, the fronts meet. Then for the second car, we'll meet probably at one third of this, and then the third car will meet at 2/3 of the first car. I mean, the next pair I'm talking. And then the fourth car again can come and meet the other car at the same front. I hope you understand what I'm saying. Okay? So if they are the same size, then this difference, the difference between this part and this part, that would be maintained. If they are of a different size, then it's not possible. There will be some kind of repetition, but it's more like an LCM. Okay? First pair will have this difference, and then maybe the fourth pair will have the same difference, and the seventh pair will have the same difference, and the 10th pair will have the same difference, but then all the other pairs may not have this difference. Okay? So you say that then they become incoherent. Okay? A coherent source, the coherent sources are like this. Okay? I mean, if you talk about cars, they must have the same size and then they must travel with the same speed. And if they do that, then they will meet at this place at the same difference. Every pair will have the same difference. Otherwise, the difference that one pair has may not be maintained by the next pair. Okay? So when this difference is not maintained, okay, I'll revert to what I did before. When you say difference, this is all right, and then if it is same, then this is also all right. This is also all right, because for the next pair also this distance will be maintained. So continuously for all the other cars, this distance will be maintained. It can be this separation, it can be this separation, it can be some other separation, but if the separation is maintained throughout, then you say that they are coherent. So, okay, I want you to understand this first. Now we'll extend the idea two ways. Okay, suppose I have a light source here. This is S1, and then I have another light source here, S2, and then I have a point in space. So the point could be this, and there is a light source here, and there is another light source here. So there are two different sources, and something may be, one source may be closer, and the other source may be a little further, or they may be at the same distance. Doesn't matter. Okay? So there are two sources, S1 and S2, and then I have this point P in space. So what is this source going to do? This is going to send out light in all different directions. And what does this source, what will this source do? Same thing. It will also send out light in all different directions. So say something goes there, here, all these different directions, and this also does the same thing. Now I am talking about this point. this point in space. Notice that there is a wave from here that will reach this point, and there can also be a wave from here that reach this point. That's a possibility. Then what is going to happen is the question. So there is this distance, and there is this distance. I'll have a wave like this, and then another wave like this. Since I'm going to focus only on these two, so I'll ignore everything else. This is just for the purpose of illustration. Okay, so I'm ignoring them, I'm just focusing on those two. Let me ignore everything else. So these two will combine here. These two waves will combine here. Now I want you to connect this with the example we just talked about. A fleet of cars, okay? Or a couple of fleets of cars. So now there is one fleet, okay? So this is like a car. So one car after another come there. Again, one car after another they come there. And they meet there. Now, I would call these two as coherent sources. S1 and S2 are coherent. S1 and S2 are coherent when they travel at the same speed. Yeah, doesn't matter. Okay, they travel. They will the same speed. Light travels with the same speed, right? This is medium. So whatever speed it says, this will automatically have the same thing. So this is redundant. I don't even need this, because unlike cars, they will travel with the same speed. So that this is a given. So I'm not bothered. Then what did he say? Then they must have the same size. Okay. What in here is the size? It is the wavelength. See, this is one, this is one, this is one, like that, wavelength. If they have the same wavelength, and if they start from the same point, then you will have, where this meets, this wave, and this wave will meet with the same difference. Okay? Suppose this wave, where is it meeting? Like maybe, say, maybe somewhere around like 3, almost like, here it's going to be 0. But this is, so maybe, it's like it's a sine 330 degrees. Is when this is meeting here. And when this is meeting at 330, maybe this is meeting at 0. Okay, this is a sine 0. So what is the difference? Difference is about 30 degrees. So the difference of 30 degrees will be maintained for all the waves. When the next wave comes, it will also meet here at the same phase difference. So you say that they have the same frequency. Why same frequency? The same wavelength. Wavelength has to be the same. If the wavelength is not the same, the first pair may meet with the phase difference of 30 degrees, and the next pair may meet with the difference of 45 degrees, 60 degrees, and then finally after a few pairs, then you will again come back to this 330. That LCM thing will work. Okay, but then you see between every pair, the phase difference changes. You don't have a constant phase difference. Okay? So that is not what you want. So the sources must have the same frequency. That should be a given. Speed is fixed, we know that. This source and this source will have the same speed in the same medium. It doesn't matter whether you bring a tube light or a cell phone light or even a gas lighter. All of them will produce a light. To produce light that travels with the same speed. Okay, so this is given. Unlike cars, this is given. But then the frequency has to be the same. And again, as I said, they must meet at the same. If you take this point, then they must have the same phase difference. Okay, this you need to have the same phase difference. Well, is it not understood? I mean, like when you have 2 point sources, does it not happen automatically? Why should you explicitly mention this? Why should? That's obvious, right? If the phase frequency is the same, if this is a point source and this is a point source, then what happens is that, like you have the phase difference will be maintained. Same size, same speed, and clearly phase should be maintained. Then why are you saying that explicitly? That's a question. The reason is this. When you have a light source, the point source is a theoretical source. In reality, every light source, even if you take your cell phone light, the torch, that would have a certain size. And what happens is that how do you get light? Because electrons get excited, when they come back, then they let out light. So, we've done that all the time in dual nature of light. So they get excited, when they come back, then it should give out light. Okay, we know that. But the point is, you have a source that has certain size, and not all the atoms in that source will get excited at the same time and go back at the same time. If you have a source like this, then maybe this atom gets excited first, then it goes back, and it's going to be at rest for a very short time, very short time, but it will be at rest. It won't get excited again immediately. But the next one can get excited. Then when that comes down, then that gives light. But you see, now it's a collection of point sources, and not all points are getting excited at the same time. I want you to understand that. It is like this. In reality, you have a source like this, not a point source, but a source which has a definite shape. And now, this source, this point, this atom has produced a wave. And then it goes to rest. It is going to take rest for a very short time. Now, this point, that's going to get excited. Okay, then this will let out light. But when this does that, you notice here the path changes. There is a small change in the path. Because the path changes, even though you see light from here, it has not come from the same atom, same source. It has come from a different atom in that source, or a molecule, however you call it. But the electrons, it got excited and then coming back. Not the same electron. Okay, it's one electron does that first, and the next electron does this first. Then the different chunks of that material do this at different points in time. So they keep doing it. So this goes up, this is gone, off, on, off, again on, off. They do it like this. So what happens is the path it has to travel to this point changes. And when that changes, even though you treat this to be a single wave, it is not coming from the same source, but it is coming from a slightly different source, so there is this extra change in the path. So you won't have, this source will not maintain this phase difference now, because there is a slight change in the path. It has to travel a little longer, right? So it travels the same speed, but then the wave will reach a little longer. For it's like this. The first wave came from this first cycle, peak and valley. First one came from this, let's suppose, and then it had to travel this distance, and like it maintains 330 degrees. But then the second one has to start from here, where there is the extra distance that it has to travel. So when this goes and meets there, it will be slightly delayed, the second one. So it's the second pair, when this meets there, it will be slightly delayed, so you won't have the same 30 degrees here. Okay, it is like this. The cars, in the car example, they go here, and the first car starts from here, and then the second car starts from here, and then the third car starts from here, and then the fourth car starts from here, okay? And then fifth starts from here, something like that. And then again sixth starts from the same position, something like that. So you see, and in this kind of a situation, can you maintain the same difference? You cannot. So even though you may think that this is contributing here, this contributes differently at different points in time. So usually this doesn't happen. The same phase difference doesn't happen. I mean, whatever I told about this is true for this. This is also not a point source. It can also have a collection of points. Then they may all differ slightly in their lengths they have to travel. Okay? So this phase difference need not be maintained. Okay? So that is why you are specifically saying this. Same frequency and same phase difference. Then they are coherent. What is the purpose of coherence? The coherence is this: you must have the same phase for all pairs. They must have the same phase. If the pairs keep changing their phases, then they are not coherent basically. So that's the whole idea of coherence. One train must meet the other train at the same phase. Okay? So this is it. So this definition is very important. You have to understand this. So when you talk about coherent sources of light, then the two sources must have the same frequency. So I told you, the cars must have the same length. And second, they must all start from the same position, the same point, because like they start at a different point, then you see, like it's even if they travel at the same speed, and if they have the same length, the next pair won't meet at the same phase difference. Okay? So the phase difference must also be there. They have the same frequency and same phase difference. So this has to happen for every pair of the waves in the cycle, wavelength. For every wavelength, this should happen. Every pair of wavelength, this should happen. Then we call them as coherent sources. This idea is very, very, very important. So what are coherent sources? Coherent sources are two light sources which have the same frequency and have the same phase difference. I hope you understand this. Now that we know what coherent sources are, let's move on to talk about interference or superposition, which causes interference. The superposition principle, which is behind the interference of waves. Clearly, you have source 1, and then there is a source 2, and then you take a random point here, P. Okay. Then there is this distance this has to travel, and this distance this has to travel, and there is a wave from here, and there is a wave from here. Then clearly they are going to meet here. So they must superpose, they must come together to create the net effect, right? Okay, this could be A sine omega t or something. So I'll say like this is A sine omega t, and this could be say B sine omega t plus phi. You can have some phase, right? Okay. So here the net wave will be y is equal to A sine omega t plus B sine omega t plus phi. Yeah. So this would be the net value here at B. I mean, if you want to see it physically, you can do that too. For example, I can draw a wave like this. Okay, something like that, and this could be like that. Okay, so there are two waves. Then, if you take this point, you need to see how they meet, how the first wave and the second wave meets there. Okay, you take point P. At point P, let's say a point at some particular point in time. I am talking about point P, right? So, particular point in time. Then, when the first wave is 0, let's say the second wave is also 0, and let's say the first wave has this kind of a structure there. Let us suppose the second wave also follows the same thing. They have the same frequency because we said they're coherent sources. And now, let's say this would be your A, and this would be your B. So at this point, when A is when the first wave is 0, this is also 0, and then this has some value, this is some other value, and when it goes to A and this goes to B, then when it comes back to 0 and this also comes back to 0, so clearly the sum would be 0, 0, 0, and you can see that these two waves are in phase. So they are in phase. Because when this is 0, this is 0, which means that phase difference is 0, right? So when this wave reaches here at say 0 degrees, this also reaches here at 0 degrees. Or if it reaches here at 30 degrees, this also reaches here at 30 degrees. Then when that reaches, it reaches at 45, this also reaches at 45. So they are always in phase. Okay. So now this will be the net effect. Okay. So this phenomenon of the waves coming together at a particular point is called as interference. And how do you find interference value? By using the superposition principle. What is superposition principle? Take one, take the other, put them together. That is superposition. So, superposition principle is what explains the interference of waves. So, what happens is that one wave is like this, another wave is like that, then when they come together, then they add up like this. So, this is called as constructive interference. They aid each other, constructive interference. Well, at the same point, something else can happen. Who says that these two waves would be meeting each other in phase? Yes, that's a possibility that something else happens, right? So, another case could be like this. Okay. So, the first wave is this. Goes like that. Second wave is exactly in the opposite direction. Like this. When this is 0, this is 0. Okay. Suppose that this is A and this is also A. The second wave also has the same magnitude. Instead of B, I am taking A. Then what would be the net? The net would be simply 0, because if this goes up to a certain value, this will go to a negative value. So when one wave tries to be positive, the other wave tries to be negative, the same amount. So then what happens is that this is a resultant. It's as if neither is there. Okay? There is no effect. At least one would have given some effect, or the other would have given some effect. They combine to produce nothing. Okay? Here, one produces light, another produces light, then light and light produces more light here. But here, one produces light, the other produces light, but light and light produce darkness. Okay? So this is called as destructive interference. And who says only these two conditions should happen? I mean, they can meet each other at any other angle, right? So that's the third condition. Third case. So this is case 1, this is case 2, and then I'm going to draw the third case. The most general case is this. Okay. So one wave is like this. Another wave is like this. Something like this. You see, they can go like this. Okay, when one is at 0, other can have some value. Then you'll have a net negative here. Notice the next negative here. We'll start from here. And you see, now this is negative, then you have positive here. Okay, so this is next point. And then both of them add. Okay, so your 0 is somewhere in between, and then your 0 is going to be somewhere in between here, and then your 0 is going to be somewhere in between here. Okay, and this is something like this. Something like this. That would be your third case. So it's the most general case, right? There could be a constant phase difference between this and this. You can see that there is a constant phase difference. They are coherent sources, right? So if this is 30 degrees, there is a 30 degree difference between these two. Then there is a 30 degree difference between these two. 30 degree difference between these two. You see, the 30 degree difference is maintained all the time. So if it was at 0 degrees, it's 30. Or 0, 30. And this is 30, 60. 60, 90. Okay, so the 30 degree difference is always maintained. So you can have this kind of a. So any type of, this is the most general interaction. And these are specific cases. When the phase difference between them is 0, and then the phase difference between them is 180 degrees. When one is at its peak, the other is at its valley, so cancelling the effect of each other. So that is destructive interference, and this is constructive interference, and this is just interference. Okay, so we want you to understand this. Okay, now we are going to focus on those two special cases, the constructive interference and the destructive interference. Now we are going to identify points where this will happen. And at all other points you may have varying phases, and you have a more general case of interference everywhere else. But we are focused on these two cases. When will you have constructive interference, and when will you have destructive interference, and how can you predict that? Would you know upfront at what point you will have constructive interference? At what other points you will have destructive interference? Can you find that? So that's the question we ask. Well, it's possible. Upfront we can do that. It's like this. Okay, I'll keep it like this, and I'll do this. This is S1, source 1. So let's say this is source 2. Again, as usual, I take a random point, right? So I take a point like this. Or I will take a point like this. P. So there is a distance here, and there is another distance. So the wave produced by this will reach it via this path, and the wave produced by this will reach via this path. Clearly, this wave will reach there first, okay, and then this will take a little longer to reach there. But once it has reached there, then the next pair, will keep reaching. That's what we saw in the case of cars, right? So in this case, let's say this is D1, or let's say this is D1, and then this is D2. So I said first two lines, so this is S1, this is S2. Because it's a shorter distance, the first wave will reach there, the first cycle will reach there, this wouldn't have reached. And then the second will reach here, that wouldn't have reached. Third, fourth, maybe fifth. When the fifth cycle reaches here, the first cycle may reach here. And from then on, you notice here, no problem. We'll keep reaching. From then on, interference will happen. Up till here, there is no interference because there is only one. There is no interference. But once the interference starts happening from this point forward, then it will keep happening for every cycle. Up till here, there is no interference. But then it's only for a very short time. Because light travels really fast. So this difference in the path can be covered very quickly. So this is purely theoretical purpose. You can see that after this point, which is a very, very short time, interference will keep happening. So you wouldn't even realize this. As soon as you switch on, you'll start seeing these patterns. You wouldn't even realize it because even before you sense, then this would have started happening. Okay, so that is what is going to happen now. Okay, so how do you predict this? That's the question, right? Okay, can I do that? Yeah, I think so. Let us suppose that I have, say, 1, 2, 3, 4, 5, 5.5 waves or something. Okay, how much? 1, 2, 3, 4, 5. Okay, maybe this is 1, 2, so 2.5 or something. So what will happen now? The first wave will reach, second wave will reach. Like the first wave will start. The first wave will start here. Here also the first one will start. Then you see after 1 to 2.5 this distance, then it will start here, right? It will reach here. And at that time, this will be somewhere here. Okay, this is there. But after this, then the next wave will reach here. Then mode will keep moving. So from when is it going to start? So that's the difference. Okay. You can probably I'll probably do 3. Okay, instead of 2.5. Let me just say that there is 1, 2, 3. Okay. 3, and then this is 1, 2, 1, 2, and yeah, 1, 2, 3, 4, 5. So 5, and then this is 3. So I can accommodate 5 waves in this path, and here 5 cycles in this path, and I can accommodate 3 cycles in this path. Okay, so note that in this picture 1, 2, 3. again 1, 2, 3. Suppose if S1 was here, then S1 and S2 would meet here straight away. The first wave of S1 will meet with the first wave of S2. Both of them would have reached this point at the same time. But it's not so. So what happens is there are two more, right? That's it. Two more waves can be accommodated there. So in this case, when the third reaches here, when the third wave reaches here, then the first wave from there reaches. Okay, so there is a difference of, you see, two wavelengths. 2 lambda. Okay, so that is how it is. So this 2 lambda is the difference between this and this. So if the 2 lambda is a difference in the path length, then you will have constructive interference, right? Because they will be in phase. They will be in phase, clearly. You can probably draw it slightly differently to understand this. S1, say S2, and then this is P, right? Okay. Let me do it this way. This is the path. I'm going to do it slightly differently. I'm going to start this here. Something like this. Okay? You notice. So what is going to be the path difference? That's the thing. This path difference will finally translate into the phase difference. You can see that. For example, what is the path difference here? It's D1 or D1 minus D2, right? D1 minus D2 is the path difference. That is this. This is D1, this is D2, path difference. And that is also equal to S1P minus S2P. And you need to see how many waves you can accommodate there. Like you can probably, like in this case, I've got 2 lambda. But that doesn't have to be 2 lambda, right? It can be 2.2 lambda, or 2.5 lambda, or 3 lambda, and 10 lambda, or 10.3 lambda, 10.5 lambda, something like that. The path difference could be that. But what happens is that if you have the integral multiple of this path difference, so integral multiple, like it is 1 lambda, 2 lambda, 3 lambda, 4 lambda, or even 0 lambda, which means there is no path difference, then what happens is that these waves will reach the point in phase. Okay, so if the path difference D1 minus D2 is n lambda, you can see that they will reach at the same, they'll be constructive actually, okay, because they'll be in phase, because the path difference is 2 lambda or n lambda. So it can be in this case 1, 2, 3, 4, 5, right? So there's a path difference of nearly 4 lambda, okay. When the fifth reaches here, the first reaches there. So the path difference of 4 lambda is there. Okay? So they will be in phase. But what if the path difference is, say, 2.5 lambda or 3.5 lambda? So when 2.5 lambda, when this is maximum, that would be minimum, because half the wavelength, right? Half the wavelength is a difference. So this would be destructive. So if the path difference is n lambda, this will be constrictive. Waves will be in phase, constructive. If this D1 minus D2 is equal to 1.5 lambda, I should say, sorry, okay, it is, 1.5 . 1.5 lambda, 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 1.5 lambda. Okay, actually it's 0.5. You can say that this is n plus half lambda. That's better. Okay, so 1.5 times n lambda. Okay, if it is like that, then this is, or I should say, no, 1 point, that's wrong. It's n plus half lambda. So that is, I've used the wrong phrase there. Okay, so if the path difference is n plus half lambda, then this is going to be destructive. When you can see that, you can see this picture clearly. It may get delayed. So after some time, reach here. But then when this reaches, it's like this. So when it is n.5, how would this be? How can I draw this first? Let's say if it is, n plus half, n plus half, not n.5, n plus half. So it is like this. So 1, 2, 3, 4, 5. Okay, when 5 reaches here, 6, 7, 8. Then what happens is, you see, it's like this. And this is 5 peak, it's not peak, something like that. So they're going to cancel kind of each other. Okay, so it's like this, not exactly aligned, so they'll be the opposite to each other. So they don't get added up, there is no constructive interference, and there can be destructive interference there. Okay, so that's how it is. And I can even put it like this. This is peak, valley, 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 like that. So now a peak, valley, peak, valley, peak, valley. You notice when it is like this, then they immediately cancel. When there is a delay, then from this point forward, you can start cancelling stuff. We're cancelling. Okay, so that is what is happening in the case of this destructive interference. So the path length, the path difference, we call this as path difference. Path difference. So this is path difference. So this is path 1, this is path 2. The difference between these two paths can be converted into a phase angle. Suppose I have something else, like the path difference is say 2.3 lambda. Then what is going to be the phase difference? The phase difference, I'm going to ignore this too. Why? Because what it tells you is that the first wave and then maybe the third wave will meet. Okay, that's what it says. That's the difference, right? It's a path difference. Okay, but then are they going to meet at at 0 with 0 or peak with peak? No, there is a slight change there. It's 0.3. So this is going to be delayed by a 0.3 lambda. So 0.3 lambda of the first wave would have gone there, and then this 0 will start. So that's the path difference between these two. Okay, so I can take this 0.3 into, what is this lambda? Lambda is 2 pi. Okay, so that would be a phase difference now, not 2. If it is 3.3 lambda, again 0.3 into 2 pi. 10.3 lambda, again 0.3 into 2 pi. So this will be the phase difference. I want you to understand this. It's not very easy, you won't understand it immediately, but think about it. If there is a phase difference, okay, clearly, the first wave will reach there first, and then the second wave will take a little longer to reach there, okay, the second source, away from the second source, a little longer. But once it is reached, then they will continue to interfere. There is no further delay, in the sense that there will always be a pair. Some pair will be there. One can be paired with 5, 2 can be paired with 6, 3 can be paired with 7, and something like that. That will happen. But then when they pair, how do they pair? Do they pair exactly constructively? There is no phase difference at all, or the second has come, the first is there, so from source 1 is there, the second is coming, but then after there is a phase difference. When this is at peak, and that is kind of, it's at 60 degrees or something like that. So, and that interference would be slightly different from the interference where everything is in phase. 0, 0, 1, 1. 90 degrees, 90 degrees. That will be different. So that is what is coming out of this. It's 2.3 lambda, forget 2. Because all it says is, after a couple of cycles, that wave will come. That's all. But once it starts coming, then the constructive interference will take place. But when it comes, it will come with a 0.3 lambda time delay. So that is what it is. So if it is 0.3 lambda, then that will translate into 0.3 into 2 pi radians. So that's the angle here. But n lambda is constructive interference. N could be 0, 1, or 2, or 3, 10, 100, 1 million, doesn't matter. You will still have constructive interference. Again, this is n can be 0, 1, 2, 3, 4, 5. Even if it is 0, then you have half lambda difference. 1, then it's 1.5 lambda. So 2.5, 3.5, 4.5, 5.5, which means then you have destructive interference. Okay, 5.5, what is the phase? Ignore the 5, 0.5. 4.5, ignore the 4, 0.5 lambda, that's the phase difference. The 4 tells you that after 4 cycles, the next wave will come. That's all it is. But when it comes, it will have a phase. That it won't meet 0 with 0. It will meet 0 with a maximum. Okay, so that's what that 0.5 tells you. So this is how you find, you convert the path difference into phase difference. So if you want to know the phase difference, if you want to know this, if you want to know how different this is from this, then you do this. Okay, take this length, then this is a path difference, right? These two are the same length, and this is extra length you have. So this is a length. Then see what is that? How many lambdas it is? Is it 2.3 lambda, 2.5 lambda, 10.5 lambda, or just 2 lambda? You find the path difference and convert that into the phase difference, as I just said here. So now you have the next equation. So you have the first equation, and then you have the second equation with the phase there. Now you can use trigonometry to combine these two. Hope this is clear to you.